Differentiate r of theta equals log base 10 of theta. Logarithms differentiate to 1 over, in this case, 1 over theta. Because the base of the logarithm is 10, the derivative rule tells us to multiply on the natural logarithm of the base, in this case, ln 10, in that denominator. It's as simple as that. Differentiate the function g of x equals log base 2 of x multiplied by x plus 1 multiplied by x plus 2 to the 3. We can differentiate the function as is, but I prefer to simplify the function. Expand by the properties of logarithms. There are 3 things multiplied together here, the x, x plus 1, and x plus 2 to 3. We can split those up as individual logarithms, and each of these terms are log base 2. Because they're all being multiplied together, we're going to string them together by addition. There's that power of 3 on that x plus 2. Also by the properties of logarithms, we can bring that 3 down as a coefficient. Now this looks easier to differentiate term by term. The awesome thing is we bypass that product rule altogether. Logarithms differentiates to 1 over the argument. And by argument, I mean whatever stuff the logarithm is acting on. The first term differentiates to 1 over x, but because we have a logarithm base 2, in the denominator of the derivative, we have to multiply on ln of the base, here ln 2. Again, 1 over that argument, 1 over x plus 1, and then multiply on a ln 2 in the denominator. That 3 is a coefficient. We just put that 3 aside and then differentiate that logarithm, 1 over x plus 2, and then multiply by ln 2 in the denominator. There is one more thing to keep in mind here. That ln of 2 actually is multiplied to the entire x plus 2. It's not like x plus a 2 times ln of 2. It's x plus 2 as a whole thing, then multiply on to ln 2. An additional but optional step here is to simplify. Each term has a factor of ln 2 in a denominator. Let's pull out a factor of ln 2 from each of these 3 terms. Differentiate y of u equals log base u plus 1 of u. This function looks really scary because not only do we have variable in the argument, there's also a variable in the base of the logarithm. I am more used to seeing a constant in the base of a logarithm. Let's rearrange this equation by the change of base formula to make this function look like something that we're more used to. We have to pick a new base on the logarithm, and there's no easier base to differentiate on a logarithm than log base e, or ln. The argument u becomes the argument in the top logarithm, and the original base goes into the denominator. Whether we have an argument or a base from the original logarithm, both of these are now arguments in the new logarithm that we have chosen. The difference is just whether we put that in the numerator or the denominator. Now that looks easier to differentiate. We're going to differentiate by the quotient rule. Ln of u differentiates to 1 over u. Multiply, then keep the denominator as is, ln of u plus 1. Subtract, keeping the numerator as is, ln of u, and then multiply the derivative of the denominator. The derivative of ln of u plus 1 is 1 over u plus 1, and we square the denominator.